Hello, everyone. Welcome to our final presentation on the analysis and redesign of the hand juicer. We are team 17, and we'll start with a little bit about citrus juicers, which is a kitchen utensil used to extract juice from citrus fruits. The bottom half, as shown in the right CAD image, is shaped so that half of the citrus juice can fit in and the juice can be squeezed out of it. This is the image of our exploded CAD with all of the part numbers associated and labeled. And the target customers through research were found that the annual demand for this product was about 1.5 million parts with the estimated production volume of 59,000 parts per year. Our primary customer group are the owners of individual home kitchens that regularly juice fruits for personal consumption at small quantities, while a secondary customer group includes small commercial kitchens that could use this part for quick slicing of fruits at medium quantities.
This is our fast diagram. So as you can see, it starts with manipulating the produce, and then it can go either one of two ways, one of them being extracting the juice through the juicing functionality and then cutting vegetables through the slicer functionality, all the while assuring dependability and convenience and pleasing the senses as well. This would be our FCMM matrix. As you can see, most of the functions that the components do are defining motion, and the lower and upper press share a lot of the same functions as well. And this would be the quad chart for each one of our parts. So the high functional importance and high manufacturing assembly cost parts include the bottom shaft, the blue coupler, the filter, and both of the presses.
So this is our functional differentiation table for our product family design. The different customer groups can use either the juicer or the slicer. So that's shown in the component commonality table, with the main changes being the upper press, lower press, juice collector, and the filter. And so those are the ones that get changed over to the slicer components. These are some of the changes. You can see the new parts for the slicer attach in the same way. This is a little bit more detail about those interfaces. The lower presses slide onto the same shaft, and the upper presses slide onto the same shaft and are attached to the coupler in the same way. This is our product family assembly diagram. You can see the delayed differentiation is when the upper press is added.
For our design for manual assembly, we chose the base plate and bottom shaft for the platform selection, the juice collector and lower press for the module selection, because these parts had high assembly times and high manufacturing and assembly costs. For our part selection, we noted that the base plate and bottom shaft shared the same function, so we saw this as an opportunity for part consolidation. For our platform part, we were able to decrease our assembly time from 7.73 seconds to 3.45 seconds, with our redesigns being adding features to facilitate orientation, providing locating features, and reducing part counts by combining the lower shaft and the base plate. There were no major changes for our part functions, where manufacturing cost slightly increases due to the material addition for our hard stat. For our module part, we were able to decrease our assembly time from 5.76 seconds to 3.95 seconds. And our main redesigns were providing locating features, reducing the part counts by combining the lower press and the juice collector, and adding features to facilitate orientation. No major changes were made for our part function or manufacturing cost. For our design for automated assembly, we decided to redesign the upper press, the handle, the upper shaft, and the blue coupler. Our redesign for automated assembly allowed our assembly costs to decrease from $5.06 to $3.95, with our main redesigns being increasing the part symmetry of the blue coupler, reducing the part count by combining the upper shaft and the upper press, and providing locating features such as an extension connection of the handle in the red coupler. No major changes were made to our part function, but our manufacturing cost slightly increases due to the material addition for the locating features.
Now we go into the process selection of the handle, and the first thing with this is learning about the associated function. And for the handle, the associated function is applying force onto the juicer. Therefore, the critical dimensions are where the handle connects with the couplers, and this is the most important because this is where you're going to be able to apply the most force with the least amount of effort. And for our tolerances, we used plus or minus 0.127 millimeters, and this is because this is the standard injection molding tolerance. We can then go into our process selection. We started with injection molding, blow molding, rotational molding, resin transfer molding, and additive manufacturing. All of those failed our specifications except for the injection molding, and therefore that became our process. Then we go into the associated function of the coupler. The coupler is used to maintain control of the juicer and define the motion of the press. This makes the dimension and location of where the holes are in the coupler the most important. This is because this is going to where you're going to properly define the motion of the juicer as it is in coordination with the other coupler, and then this will also allow for the best alignment of and ability to maintain proper control of the juicer. The tolerance that we used is plus or minus 0.13 millimeters because this is the standard machining tolerance. For our process selection, we started with sheet forming, electromachining, conventional machining, and additive manufacturing. All of these processes failed except for the conventional machining, and therefore we decided to use this process for the coupler.
Now we'll move on to the design for manufacturing. For the injection molded handle, the analytical total was $18.65. The high cost comes from the long drying time and the loss due to quality issues. The suggested changes for the part were to change the draft angles, increase the mold wall thickness, and avoid sharp angles. The drawing shows where those changes were made. This impacted the operating cost and the mold cost, totaling $1.46 in reduction in cost. This is the machine blue coupler. The cost was estimated to be $4.89 with the analytical method. The coupler was machined from a stock plate. DfM Pro did not have any suggestions for this part. This makes sense because the part was very simple and it already follows all of the design for manufacturing rules. Hubs quoted the cost to be $6.58.
As for the design of product service system, we chose for reducing negative environmental impacts to use recycled materials for the plastic and rubber components of our device. And to improve customer experience and satisfaction, we provide customers with lifetime warranty to strengthen trust and quality. And to impact both of these qualities, we individually sell replacement parts for broken components so that customers do not have to buy a whole new juicer. So the concluding parts here, we went over the amount of reductions that were saved both in time and in money. And as for design critiques, we believe that the base plate is a little too large, could be reduced, as well as the top shaft. And the handle is pretty expensive due to its shape, but that could be redesigned as well in the future. Thank you very much.